We went through a set of assumptions, a checklist, if you will, last time, for a single proportion confidence interval. The set of assumptions was that, number one, we have to have a simple random sample. That's still valid over here. We still want to do as close to a simple random sample as we can. Now, granted, mine was not simple random. It was simple-ish, random-ish. But it was as good as I can do being in town, not being funded by the government. Basically riding my bike past El Taco. Did as good a job as I could. The next assumptions over here, do you remember what the next few assumptions were to use this test? Think 243. What did the experiments all look like over here? What distribution from 243? Starts with a B. Back up even more. Drew, the binomial. They had to be binomial. You had to run an experiment that had two outcomes. Heads, tails. Foreclosure, not foreclosure. Heart attack, no heart attack. That's what we're testing. So, the assumption here was binomial. The assumption over here is continuous. So theoretically you can think normal, but it's actually T. But they're both bell curves, so they're continuously bell-shaped. That's one thing you should test. There was a sample size restriction down here too, which I'm never going to test you on, that whole NP bigger than 5, NQ bigger than 5 thing. Okay, I'm much more interested in you calculate the sample size using the program. But you really should. I don't care about the 30. That is irrelevant to me. The 30 is irrelevant. What I care about is to make sure that your data actually roughly looks bell-shaped. Guys, grab your TIs. I want to take a look at this data. Now we're kind of doing this in a backwards order. We should actually check the data shape before running the interval. Because if the data was horribly misshapen, we probably shouldn't have run that interval. And I'm going to ask you why in about 2 minutes, and hopefully you get some responses for me. So let's take a look at it. Yes, I know. Remember how to turn a histogram on? If you say no, let's go through it.
No.
Second y equals, I'll also swing the camera over so we can see this. Second y equals gets you to the stat plots menu. Turn her on by pressing enter, and then just looking and making sure the word on is highlighted. Cool so far? Under type, press down and then scooch over until your histogram, which is the top right corner, is highlighted. It's a little bit different than 89 back there, Danielle, I apologize. And the histogram is the one thing I have a hard time with on there, but we might be able to futz through it. XList and freak, you have to set this to be the same as it was for T interval, so it's going to have to be L1 and 1. L1 and 1. If anybody's getting Y instead of 1, make sure your alpha button is off. I don't know why, this is a bug. Whenever you jump into these lists, see how the alpha button is blinking? Just turn that off by pressing the green key and then type the number you want. Then you'll get 1 and not Y. Everybody golden? Graphs on, histogrammed, L1 and 1. One thing you should do is real quick press your Y equals button and make sure there's no equations in here. Shouldn't be any equations turned on. There shouldn't be anyway from 243. We didn't ever use it. We never use equations in there. Once you're golden, zoom 9. Zoom 9. Get you a graph. Now, this is the default graph that TI selects. You can futz with it. I like to futz with it. I think that's too few bars in most cases. Remember how to futz with it? You can say no.
No.
I think we talked about this before. We talked about this a couple days ago. Well, actually, you can do that, but I think it's easier to press the window button and change that X scale to a different value. Change that X scale to a different value. You can also change the X min and X max if you want to. But I like to start with the X scale and refine it from there. If I want to make more bars, I need to make the X scale smaller. Because right now it's too big, and the X scale is a measure of how wide the bars are. So if you drop that down, say you make it 0.015, and then press graph, you'll notice I didn't make it small enough. The shape did change, but I had the same number of bars. Actually, I picked up one more over here, it looks like. So I'm going to make it a little bit smaller. Maybe make it 0.01. And then hit graph. Okay. Now you can keep messing with this. You can keep messing with this. But what do you notice as you keep messing with it? Make it 0.05 maybe. Or 0.005. Right. Would you describe this data as bell-shaped? It's hard to make a call, isn't it, Will? It's hard to make a call on it. I mean, you could eventually shrink it down so that you could argue that could be bell-shaped with a larger sample. You could also argue that no, it's not, and not only is it not bell-shaped, but there's this goofy guy out here who might be a what? He might be an outlier. Might not he be? Might not he be?
Might not he be, yes. This might be an outlier, and why do we care about outliers?
No, seriously, why do we care about it? Why do we care about it? Why would that be a big deal?
Because those skewed data.
Boom! We are talking about an average now. Averages are those ones. I love averages, and they're great, and they're unbiased estimators. But the problem is the average chases the outliers. Do we have a way to measure whether that's an outlier or not? We have a way, don't we? Let's put a second curve on top of this one. Okay? Back. Second y equals. Second y equals. Leave plot 1 on, please. Leave plot 1 on. But turn on plot 2. Who remembers? L1, second one. Second and then the number 1.
This is the box.
Yes, ma'am, Rosie. We're going to go for the box plot. And mine's already selected down here. It's this one right here. It's called the modified box plot. It's the one that shows outliers if there are any. It's this guy down here. All right, so he's already selected for me. My L1 is what I want with a frequency of 1. Good so far? As far as the mark, what that will be is if there are outliers, it'll use that symbol to mark them. I think these exist on the 86. We'll take a look, Kayla. We have some time. Good so far? When you're ready, just hit graph. Don't hit zoom 9 again. If you hit zoom 9, you're going to lose all that window work you did. So just press graph. How do we feel about that data point? Is he an outlier? Is he an outlier? He is not an outlier.
No.
And this brings me full circle to what I was talking about over here. The assumptions that should be met about this, in my opinion, are a little misguided in most stat textbooks. Most stat textbooks, let's swing back over here, will tell you that you have to have at least 30 data points in order to use the t interval. Or excuse me, if you have between 2 and 30, you can use the t. I don't care how many you've got. There are 2 other things I look at. I look at whether or not the data is arguably bell-shaped. And that concerns me a little bit. But you'll see very, very soon, i.e. second project, you'll see very, very soon, i.e. second project, that the shape is not as important as the presence of outliers. Because the presence of outliers yards the average towards the outlier and effectively makes one data point more valuable than others. Does that make sense? You guys buying that? It effectively makes one data point much, much more powerful and valuable than other data points. Because what will that outlier do? It pulls the average, but what does it also artificially inflate?
Margin of error.
Yes! If you have a wicked outlier, say somebody made a Del Taco, a half-pound bean and cheese burrito, and it was only a quarter pound because they were talking to somebody and they squirted the beans in and it wasn't right. And I took it home and weighed it, and I'm like, oh my god, it's a quarter pound. I put that quarter pound in. My standard deviation is no longer whatever the TI said it was. It's now much larger because of that one. Because that one data point is being overly represented in the margin of error, in the standard error margin of error. Or if I measure it wrong. I had a hell of a time for a while. I measured the first couple weeks worth of the burritos. I was putting the scale on top of Travis's guitar amp, which was covered in felt. And you can't do that with those highly precise scales. I didn't know this. They have to be on a hard surface. So I used his guitar head, which I had a hard surface on, and that worked just fine. But I was getting goofball numbers, like this burrito weighs 20 pounds. I'm like, well, it feels like it when I eat it, but I know it's not 20 pounds, right? So outliers can be due to a whole host of things. Measurement errors, goofy data points that are non-representative. And the problem when you have small data sets is that an outlier in a small data set does a hell of a lot more damage than an outlier in a large one. As a matter of fact, you expect outliers in large data sets, don't you? You expect them. Think about the bell curve. 3 standard deviations. 3 standard deviations traps 99.7% of the data. Now, if your data set's only, say, 20 or 30 large, you might not have any in there. But all of a sudden, when you're talking about a data set of 100 or 1,000 or 10,000, you take 99.7 of 1,000, and that's 997. You expect 3 outliers on average. You expect 30 outliers out of 10,000, 300 outliers out of 100,000. This is why companies went to Six Sigma. If you've ever heard of Six Sigma, anybody heard of Six Sigma? I'll stop talking about it then. But that's the point. When data sets get very large, outliers are almost a mathematical certainty because the chance of having no outliers shrinks to essentially 0. 0.997 to the 10,000th power is basically 0, which means there's 0% chance they're all inside 3, which means at least one is outside with 100% certainty. Does that kind of make sense? That's a lot of 243 review in one tiny time interval. I apologize for that. So, recap. Start and stop again. Start and stop again. You guys are getting that